This video is going to help us learn how to calculate the confidence interval of the mean as opposed to the confidence interval of the proportion from a previous lesson. And it will also help us learn how to apply margin of error to calculate a sample size needed for a survey. So confidence interval for a mean with a known standard deviation, it is also then the z-interval as we've previously learned. So a couple of things of information here. If we know the standard deviation, the Greek letter sigma, then we use the z-interval method from yesterday's lesson, from that previous lesson that we've learned. Right. What is the confidence interval for mean used for? It is used to estimate the mean of a population by using the sample mean. So we can estimate the mean of the whole population by using a mean of just the sample. If we take an SRS from a population, we will get an X bar. We will get a mean of that sample as an estimator for the mean of the whole population. All right, this interval that we are going to create, X bar plus or minus the Z interval times this new looking fraction. It's a little bit more simplified than the previous square root formula we had, but what I'm highlighting now, this is the math process that will allow us to calculate this 95% confidence interval for the mean. Again, that X bar, that's the mean of the sample, plus or minus the Z interval times the standard deviation divided by the square root of n, which is the sample size. We still have this confidence interval table on the right. So depending on what level of confidence we want to use, again, 95% is typically the one used. But if it's 80, 85, 90, anything on this list, we use the matching Z interval factor. And that's what the second note indicates. The Z interval we use from the chart will allow us to make a statement about how confident we are that the intervals will capture the true mean for the whole population. What's important is we cannot say there is a 95% probability that the population mean is in our interval. We can just simply say how confident we are that it will be there. So it's a little weird, but just be careful that we cannot say anything dealing with 95% probability. Right. A couple of requirements that must happen for this process to even take place. Requirement number one, we must have an SRS from a normal population, and it will indicate that in the problem, or our sample size must be greater than or equal to 30. So 30 is that magic number. If it's not greater than or equal to 30, and it's not an SRS from a normal population, then we cannot go through this 95% confidence interval process. We also must know the population standard deviation. So those are the two requirements needed for this process to work. As the last several lessons have gone, this is a systematic process approach. We learn step 1, step 2, step 3, step 4, and we can baby steps through the problem and be successful. Right, so example number 1. In a random sample of 60 college students, so check right there automatically, 60 is bigger than 30. So automatically with that first half of that sentence, we know that we meet requirement number 1. It was determined that the average credit card debt was $727. From previous studies, we know the standard deviation of credit card debt for all North Carolina students to be 141. There's the second requirement. We know the standard deviation. Calculate a 95% confidence interval, CI for confidence interval, for the mean credit card debt for all North Carolina students. So requirement number 1. Requirement number 1, n equals 60, which is greater than 30, greater than or equal to 30. So check. Requirement number 2, standard deviation. We must know the standard deviation of the population. The standard deviation is $141. Check. So we know those two things. Those are the only two requirements we need to know. Is it an SRS from a normal distribution, or is the sample size greater than or equal to 30? So, and then secondly, do we know the standard deviation of the population? When we know those two things, the math behind it becomes fairly straightforward. So our 95% confidence interval, 95% confidence interval, the formula that we have in our notes is going to be 720 is the mean plus or minus, and then it's the Z score. I'm sorry, the Z interval, Z with that asterisk, Z interval times our standard deviation divided by the square root of our sample size. So all I'm doing here is I'm putting words to that formula that we had previously in our notes. So it's real easy for students to get lost in all the different notations and all the different symbols. So I like to put words to those symbols. Right? So if we read back through the problem, do we know what the mean is for this problem? It was determined that the average is another word for mean. The average credit card debt is $727. We're going to add to that the Z interval, 95%. The Z interval is 1.96 from that chart, times our standard deviation of 141 divided by the square root of that sample size divided by 60. And so now I can go to Desmos and crunch the numbers. All right. If you want to try to do this almost all in one step, you can. I'm going to try that here. 727 plus, actually I'm going to do the minus first. 727 minus 1.96 parentheses 141 divided by the square root, and then our sample size of 60. And I just want to carefully make sure I've typed it in right. 727 minus 1.96, and then inside the parentheses is that formula, the standard deviation divided by the square root of the sample. Did I type that into Desmos the right way? 727, I'm doing the minus first, so I want to get the lower limit number first, minus 1.96 times, and I'll go ahead and make it easier for us here. Instead of using the X for times, I will use the parentheses, just like I typed into the Desmos. So I feel good that I did type that in correctly. That gives me this lower limit number of 691.32. And the reason that I'm just going 0.32, because we're dealing with money, and our money only goes to two decimal numbers. So the lower limit number is 691.32. And to get the upper limit number, I just simply need to change the minus to a plus in Desmos. So if I go back and change that minus to a plus, I now have the upper limit number, 762.68, rounded off to two decimal positions for money. 762.68. Right. Now let's make like we did in the previous lesson, let's write out, let's make a conclusion statement. So my conclusion statement, we are 95% confident. You go ahead and make this a little bit smaller. We are 95% confident the true mean, since we're talking about the confidence interval of the mean, the true mean credit card debt for North Carolina students, North Carolina college students is between $691.32 and $762.68. Now, we can't say that there's a 95% probability that the mean is in that interval. We can just simply say that we are 95% confident the true mean credit card debt for North Carolina college students is between those two numbers. Example number 2, slightly different setup, but the same process. U.S. newborn birth weight is normally distributed. So normally distributed, check. That's the first requirement. So number 1, normal requirement number 1, normal distribution, check. Requirement number 2, do we know the standard deviation? That's what our sigma symbol is right here. Sigma equals 1.25. There is our normal distribution. There is our standard deviation. Standard deviation equals 1.25. Check. So we do have both of those requirements. Now, one thing about this problem we don't know what the mean is. Right? We don't know what the mean is. However, we can calculate the mean using our data. So again, one way to calculate the mean is add all this up, divide by how many there are. In Desmos, what I find to be an easier way is to type in mean and then type in all of the numbers separated by a comma. So if we type in our numbers, 6.3, comma, 6.9, comma, 7.3, comma, 7.7, comma, 7.9, comma, 8.5, comma, 9.5. So I've calculated the mean of all of that data, and we've calculated the mean to be about 7.73, 7.729. I don't know if there's a difference in how many decimals. I'm going to go 3 decimal positions since we're not talking about money. So I'm going to use 7.729 as the mean. So mean our mean equals 7.729. I have everything I need to now create this 95% confidence interval about the mean. Right? So my formula to create the 95% confidence interval. 95% confidence interval is the mean 7.729 plus or minus 95%, so I'm using my factor 1.96 times the standard deviation 1.25 divided by the square root of the sample size. Right. What is our sample size for this problem? Well, lo and behold, 7 newborn babies were chosen at random. There is our sample size. There is our letter N. So divided by the square root of 7. Now I can go back to Desmos, let Desmos crunch these numbers for me. I just need to know how to use the technology available. So 7.729, I'm going to do the minus first. I like to do the lower limit first, minus 1.96 parentheses, and then our standard deviation 1.25 divided by the square root, and then the sample size 7. And then close that parentheses out, and we see the lower limit number to be about 6.803. Again, continue to use 3 decimals on this one. So my lower limit number, 6.803, and then I simply go back and change the minus to a plus, and this will give us the upper limit number. 8.655 as that upper limit number. 8.655. So this process is a whole lot faster than some of the things that we've learned about in the previous lessons. But they all kind of build up on each other. So our 95%, the conclusion, the statement that we can make. We are 95% confident we are 95% confident the true mean birth weight of all U.S. babies is between 6.803 and 8.655 pounds. There is our conclusion. There is our judgment, our inference that we can make after completing our analysis and our statistics. Example number 3 will be the last one dealing with this 95% confidence interval. Then we'll look at that margin of error concept. So the history department at major university is concerned that college students do not understand world events, and unfortunately that's all too often the case. A standardized test was given to 30 students. So there's our sample. Is that greater than or equal to 30? Yes. So requirement number 1. Our sample greater than or equal to 30? Yes. Requirement number 2, we'll find out in a minute. Do we know what the standard deviation is for this? So standardized test was given to 30 students. The sample mean was 58 points. It is known from multiple years of testing that the standard deviation of all students is 3.2. So we do know the standard deviation, 3.2, check. So we have the 2 requirements that we need. It tells us the mean is 58. But notice a little curveball thrown here. Create a 99% confidence interval. So we don't want to get in a rut of always using 1.96 without reading the problem carefully. 99% confidence interval will give us a different number from that z-interval chart. All right, so we're not dealing with a 95% confidence interval. We're dealing with a 99% confidence interval. So our 99% confidence interval, it doesn't change the approach that we take. The mean of 58 plus or minus, instead of 1.96, when I go back to the first slide, what is the factor from our chart when we're wanting a 99% confidence interval? 99% confidence, then we're going to use 2.576 as our factor. Now, some people are going to get mixed up. I don't know what to do. All I've done is pick the correct factor number, 2.576, off of that chart that's provided. 99% confidence interval is 2.576. Parentheses, the standard deviation of 3.2 divided by the square root of our sample size, 30. Now I can take that information to Desmos and let Desmos crunch those numbers for us. All right, so in Desmos, we have 58 minus, so I can do the lower limit first, 2.576, parentheses, 3.2, the standard deviation, divided by the square root. SQRT is a fast way to get square root in Desmos. The square root of 30. So our lower limit number is about 56.495. We can call that 56.5 will be good. About 56.5 is going to be our lower limit number. And our upper limit number, just simply change the minus to a plus. Minus, change to plus. Our upper limit number, about 59.5. Now we can make our conclusion. Our conclusion statement. We are 99% confident the true mean score of all college students who took this test is between 56.5 and 59.5. There's our conclusion statement. That's our 99% confident statement about the mean of this problem. Right. The next objective that we had listed was to apply margin of error to find sample size. So margin of error just means that we understand that the numbers we create may not be exact. There's always a margin of error when statistics are involved. So the notation that we have, M equals, M being margin of error, that Z interval times that fraction, standard deviation divided by square root of N. So if we are going to try to find sample size, it really helps us out to rewrite that formula for the letter N, since that is our sample size. So if we manipulate that formula, rewrite it, and we can rewrite that formula, N equals the Z interval still times that standard deviation divided by the margin of error and then squared. The square comes from canceling out the square root. So that's the formula for it using notation. To the right, you see where I have that typed out using words to make it more comprehensible. Z interval, that Z asterisk, that's the Z interval times the standard deviation, divided by the margin of error that we're trying to accomplish, and all of that quantity then squared. Right. There's different ways that we can reduce margin of error. We can lower the level of confidence. So a 95% confidence, okay, let's drop it down to 90% confident. Then we can reduce the margin of error, or 85% confident. So when we reduce our confidence level, that gives us a chance to reduce the margin of error. Another option is we can increase sample size. And the third option, which is probably one of the more complicated, is to find a way to reduce the standard deviation. So the main focus we're going to use for today's lesson is to take information given to us and try to calculate what sample size is needed for that problem. Right, so we're going to basically just be using this form that I'm circling now, that form of our margin of error concept. So we've had our recent presidential election. So suppose that for a presidential election poll, the known standard deviation is 50. What sample size would you need if you want a margin of error of 3 points and to be 95% confidence? Okay, so 95% confidence means that we're going to use 1.96 for our Z interval. A margin of error of 3 points, there's our letter M. Standard deviation of 50, that's our Greek letter sigma. So if I just simply plug these into our formula, and we'll see that this process, it looks weird, but it's pretty straightforward. So our sample size N equals our Z interval 1.96, since it's 95% confident, times the standard deviation of 50, divided by the margin of error that we want, 3 points, so divided by the margin of error 3, and then simply square that. So I think we have the luxury in Desmos to type that in just like it looks, being careful with parentheses. So let's see if we can do that. Right, so let me clear that out, and let's type this in and see if it lets us type it in. Starting with parentheses, 1.96, parentheses 50, close the parentheses out around the 50, divided by, see how it divides both of those? So divided by our margin of error that we're targeting, 3, and then move to the right side, close off the big parentheses, and then square. So 2 ways we can get the square. If you click the keypad, then it's the A squared button, or you could do Shift 6 and then type in the square. Right. So this tells us we need a sample size of about 1,067 people to meet our goal, a margin of error of 3 points, and then a 95% confidence level. So our sample size, really, it just needs to be at least 1,067. If you increase that sample size, then you might get a little bit better than 3 point margin of error, maybe 2.6, but 1,067 would be the minimum. All right. So letter B, what happens if we change and we want our margin of error to be 2 points? Now, a 2-point margin of error means we want it to be better. So what sample size would be needed if we changed our margin of error to 2 points? So n equals, the same numbers are going to hold true, 95% confident, so 1.96 times our standard deviation of 50 divided by 2, that's our target margin of error. And then go to Desmos, make the necessary changes. And what we're going to see is with a smaller sample size, a smaller margin of error that we're targeting, we're going to see how that affects the sample size needed. So if I change that 3 in the bottom to a 2 for margin of error, we see that the sample size has increased drastically. We now need a sample size of 2,401 to accomplish our goal. Next example that we're going to practice. Right. Suppose for a new marketing campaign, Under Armour wants to claim that people prefer their brand over Nike and Adidas. If the standard deviation of their survey is 15 and they want a margin of error of 2 points at 90% confidence, what sample size is needed? So notice we've lowered the confidence level down to 90%. If we're down to 90% confidence level, what factor do we get off of our Z interval chart? So let's go back to the first slide. At 90% confident, we're going to use the factor 1.645. So 95% is commonly the one used. So make sure we read problems carefully when it changes to a different confidence interval. So we're dealing with 90% confident. So again, 90% confident, we want to use 1.645 as our Z interval. So our Z interval, 1.645. N equals, and it is that Z interval, 1.645, parentheses, the standard deviation is 15, divided by the margin of error that we're targeting, a margin of error of 2 points, and then we square that. So when I go to Desmos, I already have the kind of the template set up for Desmos. I just need to change the appropriate numbers instead of retyping everything. 1.645 is the Z interval. Our standard deviation for this problem changed to a 15, and we want a margin of error of 2 points, so the denominator stays 2. So we need a sample size of just about 152 samples. So for them to be able to make their claim, they need a sample size. If they choose a sample size of about 152 people to survey with this information, they should get a margin of error of 2 points, and they should be at the 90% confidence level. Our last example for this video with margin of error. Suppose Apple is in the developing stage of a new camera for the iPhone 15. It won't be too long when that phone's coming out. The developing program has a standard deviation of 3.7. They want a margin of error of just 1 point. They do not want a big margin of error, just 1 point, and they want to be 95% confident of it. What sample size do they need? So N equals 95% confidence is 1.96 for the Z interval times the standard deviation, 3.7, divided by 1, and then that squared. So their sample size that they need to use to create this situation, 1.96 times 3.7 divided by 1 squared, should be pretty straightforward. 1.96 times 3.7 divided by 1 and then squared, 52.59. I'm going to call that 53. I'm going to round that up to 53. So they need a sample size of 53 to accomplish what they want to accomplish. As always, I hope this video has been helpful for you.